Laboratory 4 considers a solid body, namely a gear tooth. The tooth itself has roughly equal dimensions, so there's no thin direction, which allows us to view it as a plate. I assigned this as a project to a graduate student who was my assistant in my on-campus finite element class, Roland Cass, and he worked diligently and came up finally with a Spur gear model. I simplified it to 2 elements in order to minimize the data entry and then the actual cost of running it on a mainframe computer. We'll follow the normal pattern of looking at physical modeling first, then we'll consider the finite element modeling. I'll show you the data sets for 3 typical commercial finite element codes, and then we'll consider the results. The gear itself could be indeed stamped or machined from solid plate, but when you concentrate your attention on the tooth, then you're looking at quite a little small blocky body. The gear will be taken to be 10 millimeters in thickness and to be formed as shown in this view with the 100 millimeter pitch radius. That's the line of contact with the adjacent gear, and then 110 millimeter outside radius. Now, this gear is cylindrical in the general sense that the body can be swept out by straight line generators parallel to an axis here. Let's concentrate our attention on the tooth itself and consider what would happen in the stress field in the 2 cases. One where the gears are perfectly aligned, neighbor to neighbor, and then one where there's a misalignment such that the force is transmitted out at the outer edge of the gear tooth. Here I sketch the tooth, and in the first case I'll take a 600 newtons per millimeter running load and consider to be the result of 2 gears perfectly meshing, or perhaps gears that have worn in over some period of time. Then the eccentric or the misaligned force will be the full 6,000 newtons acting at the extreme edge of the gear tooth, and this is at the pitch radius. Now, to simplify the problem, we'll assume that the loads are acting in the y direction in a basic coordinate system so that we don't have to split the loads into components. Here's a sketch of the cross-section of the gear tooth, and I give the coordinates here. Now, they're also given in tabular form, and I'll show those in the data sets for the 3 codes, so I won't bother to clutter up the notes with an extra copy of the coordinates. But the pitch circle is shown here, and the gear itself then will be modeled down into the base region to some extent. We would expect that the stresses would be highest probably in the neighborhood of the contact point, plus extending into the root area to some distance, although at some point where the gear broadens out, and you can see this would continue into a circular notch here, then the stress is diffused out into a much greater region. So we'll take a very simple model of this, and we'll put one element in the upper region here and one element in the lower region, with the bounding line being here at the pitch circle. The gear tooth is a pretty chunky piece of steel. It's roughly 10 by 34 by 24 millimeters. Therefore, we'll treat it as a solid body. I've mentioned before that we'll assume that the forces at the contact region are directly in the y direction. We'll extend the model down into the base of the gear a little bit beyond the expected high stress region. Then we need to do something about the boundary conditions. Because the disc is relatively strong compared to the teeth, I think I'll consider that the tooth is perfectly clamped around the base. Probably if this were a commercial problem, though, you'd extend your model out a little further so as you had some measure of the elasticity of the disc itself. Lastly, we should assume at this point linear elastic material and small deflection so that we can use a linear theory, but we have to check this at a later time and make sure we don't exceed the limits of the theory. Now, the reason I say we should, this is a body that should operate under relatively low stresses because fatigue is a potential failure mode. So you wouldn't want this to be operating up in a nonlinear material region where you were plastically deforming the body. There is in gear theory, though, some feeling about distributing that load along the tooth. Some gears are made that are crowned in that region so that the load automatically starts out at the center of the tooth. But then the gears can wear in, and indeed there could be some kind of surface wear that would help them adapt each other. Now, we're not going into that detail in our physical model, just for purposes of our academic study here. For finite element modeling, we have made the decision to model this body with solids. And there are several solid elements available in each of the codes. I'm going to choose a 20-noded isoparametric solid, which means that the physical element will have to be mapped onto a double unit cube in the C eta zeta space, and that mapping will mean that you can't distort the elements too much. Here's our model, and it will turn out that these elements are okay. These can be mapped onto a cube. We'll number the grids bottommost first and then spiraling toward the top. Of course, the grid numbering is different from the connectivity numbering, which will follow, and is different in the different codes. I'm showing the eccentric load case here. We've put the boundary between the elements to lie on that contact line here and to lie at the pitch radius through the interior. The coordinate system is perhaps strange, but it's the one that people in the gear industry like to use, with X outward, Y in the direction of load, and Z transverse. Many commercial codes don't have the capability for equivalent nodal loads on a line load acting on a solid. That makes sense because the concept is a little vague. That load would be singular in the sense that the area on which it acts is indeterminate. Now, we're doing an academic study here, so I'll consider that kind of loading. And of course, the point load also is a bit indeterminate because it also has no area on which it's acting. So it's not possible to push this problem far and come up with a real fine mesh and get some exact answer for the problem because it's a singular loading situation, much as the geometry was singular in an earlier problem that we had where there was a reentrant corner. But I'm going to create equivalent nodal loads in a homemade way by doing the line integral on the z-coordinate running along this loaded line from -5 to +5 millimeters. Then the three-dimensional force field has only the y component of 600 newtons per millimeter, and then we must use the shape function and evaluate it on that edge. Now, from previous problems, it's known that what we're doing really is a parabolic distribution of the load, and I'll immediately jump to what's called Simpsons Rule, which distributes those loads in the ratios of 1 to 4 to 1. So the middle node actually picks up the bulk of the load, which is surprising when you first see that. The user could prove this, though, by passing parabolas through those three grid points that are loaded and checking out that this inner product here is correct. And of course, what this is basically is the ability of that distributed load to do work on each of the three shape functions in question at those three home nodes. We'll now turn to the creation of data for commercial codes. The first data set is for the MSc NASTRAN program, and the connectivity approach for the 20-noded hexa element is to number the vertices on one face, say the bottom one, 1, 2, 3, and 4, and in that order. So it's looking from above, it's counterclockwise, but from below, it's clockwise. Then you progress up to the top surface and go 5, 6, 7, 8. Then you pick up the middle nodes on the bottom surface, 9, 10, 11, 12. The middle nodes on the rising sides here, 13, 14, 15, 16, and finally the mid-side nodes on the top surface, 17, 18, 19, 20. And those are listed down below here in terms of the actual numbering of the grid points for the two elements. The first statement in the MSc NASTRAN dataset is a file management statement, and we're going to use ideas for our post-processing this time. We'll ask for the data file to be set up for the post-processing through output 2, and we'll name the file lab4.f12. Our executive control statements, again, we use SOL 101, the linear static solver, and allow 5 minutes. We're going to run this on a Hewlett-Packard 700, so it will do the problem really in a matter of seconds. We'll ask that we echo back only the sorted data, and then we ask for displacements, stresses, SPC forces, and element forces. Now we could also ask for the O load, which would echo back the loads. Because we don't have distributed forces here, I didn't feel it was necessary because it would only echo back the concentrated forces that we put in. But it is a check to make sure that you've entered your forces correctly. We're going to use 2 load subcases in this run. MSc NASTRAN allows subcases to differ in loads and boundary conditions. That can be very useful because in the boundary condition case you can study symmetric and antisymmetric solutions and add them and so on. For our case of loads, we call out arbitrarily a number 21 to be referred down below as the aligned set of loads. Then subcase 22 referred to down below will be the misaligned load. Then we start our bulk data, and here's our param card where we're setting the post-processing for ideas. I will turn on the auto SPC. We'll try to head it off, though, by constraining throughout the whole body the degrees of freedom 4, 5, 6, which are the rotations at the elements. And rotations are not defined for such an elastic element. The grid points are rather standard. The ones I'm showing here so far are at the root and are going to be clamped. So you'll see the permanent embedded single point constraint list in the 8th field. The next figure is entirely filled with grid points. Not too exciting. We are using the basic coordinate system both to define the grid locations in entering data as well as the reference for the internal calculations in the output. The grid definitions are concluded in this figure, and they don't have any constraints included in the 8th field because those are out on the free edges of the gear tooth. Now the connectivities are given here. We have the 2 elements, 1 and 2. It takes 3 cards to describe all 20 grids. The elements point to a P-solid card down here, number 30, and then the P-solid card in turn points to a material card. The only noteworthy thing here is that I'm calling out for a basic coordinate system as the reference for our stresses. If you don't do that, you get a material coordinate system. You can also have an element coordinate system here, but the defaults are not useful typically on this particular solid element. I much prefer to have the basic coordinates as the reference because I know where they are. The element coordinates are more difficult to define, if not impossible. Then the material card is a Young's modulus for steel. We leave out shear modulus and we put in Poisson's ratio. I'll enter the forces in this figure. They're intermingled a bit. I've chosen to enter them grid by grid, and so the three forces for the aligned case are these, and then the misaligned force is here. The coordinate system will be the basic coordinate system. We'll use a magnitude factor here of 1, and then this is the x force component, the y force component, and the z force component. And then that's the end of our data. Now I've been running on an Apollo 3500, which is just about to be retired, but I submit the actual execution to a Hewlett-Packard 700 on a network at the University of Michigan, the Computer-Aided Engineering Network. Now we'll talk about the results in the next few figures. The deflection field for the aligned load case has a bit of the appearance of a cantilever beam bending under a lateral load, and I'll show that figure later at the end when we compare the three codes. The maximum deflection is out at the free end of the gear tooth. Actually, nodes here 26 and 30, and these have this 0.13 millimeter deflection. The maximum deflections in the x direction, which is vertical, are at grids 22 and 23, which are also mid-side nodes, but just one layer of nodes away from the applied load line. The misaligned load causes a much more intricate deflection pattern. The maximum y displacement is under the load, as you might imagine, at grid point 15, so it's right at the point of application. And it's about twice or 2.5 times as big as the aligned deflection was up at the tip. The maximum x deflection, interestingly, is at grid 19, which is diagonally opposite on the back side of the tooth from the load application point, but it's not large. Let's look at the stresses in the hexa elements. MSc NASTRAN reads these stresses out element by element with the element number on the left. I'm mostly interested in the von Mises stress for our particular study. We get a value of 173 megapascals here at the grids 15 and 17, which are on the pitch radius. So they're the outside nodes. Actually, the ones with the smaller loads, if you remember. Then from the upper element, number 2, we get much lower values that are estimated. It's conventional then to average these two numbers to arrive at some average stress, and I show that down below here, 142 megapascals. The stresses that result from the eccentric load are a fair amount higher. This time the highest stress is at the 15th node, which makes sense, that's where the load is applied. And the predicted value within element 1 for that node is 631 megapascals, whereas the predicted stress from element 2 is this 496 megapascals. You can average those out and get 563, and that's quite an increase. It's more than 3 times the stresses that were in the aligned gear tooth problem. Now let's turn to the MARC program and redo the problem using MARC. We're going to use two number 21 solid elements in MARC, and the grid connectivity pattern is shown here. This is the same, it turns out, as the MSc NASTRAN one, where you start at a node on one of the vertices, numbering as shown, which is counterclockwise when viewed from above, or clockwise when viewed from below the element. Then you progress to the opposite face with 5, 6, 7, and 8. Then you pick up the mid-side nodes 9, 10, 11, 12, 13, 14, 15, 16, and finally 17, 18, 19, and 20. So there's a definite pattern, and you have to get that right, otherwise the elements get turned inside out. Some of the control statements are given here. It's good to give some titles that remind us of what the problem was intended to do. The sizing number is nominal for this small problem. Here are elements 21. We're doing an elastic stress analysis. Then in our post-processing, we'd like to get these components of stress read out. The default for this solid element is to read out the stresses at the Gauss points. So when we want to get nodal values, we have to ask for those. And that's the purpose of this first set of some 4 cards here, to print node, and then one set of requests following. And I'm asking for total displacements, loads, reactions, stresses on grid points 1 to 32. So this will help us get tables of the von Mises stress at the node points. Otherwise, it would be only at the Gauss points. Then our load cases given here. First we give only the load case number 1, then later on we'll follow up with a second load case. That's the way they handle it in MARC. We give here the distributed load that has been turned into equivalent nodal loads earlier. And it's 1,000 and 4,000 and 1,000 newtons in the y direction. So we have here the x, the y, and the z translational components here in each case at the grid points 15, 16, and 17. It's interesting, in MARC they have the grid point following the value of the load. Then we're going to have fixed displacements. We have one set of these constraint cards. We're going to fix the coordinates to not move in the x, the y, and the z directions. And we're going to constrain those degrees of freedom, which are numbered 1, 2, and 3, and they're going to take these values. And the grids in question are 1 through 8. Those are the ones lying at the base of the gear tooth. Then the connectivity cards here, there are 2 such sets following, and here are the connectivities as we showed earlier in the connectivity diagram. The solid element in MARC exists in a 3-dimensional space. There is a request for how many degrees of freedom per node here, but it's apparently ignored by the code from what I can tell from the serious users around here. So this 6 is generally overridden by the element type. There could be as many as 6 degrees of freedom per node, though, in general, and there are 32 such nodes involved. Here we have the numbers for the node points, and then here are the x, y, and z locations. And this and the next figure are completely full of such coordinate points. And this next figure is also filled with these coordinates. Let's now write out the material, geometry, and load information needed for the second load case. On the material side, this is an isotropic material. We'll have one such data set entered. We arbitrarily give it a number of material, number 31, although that's not used anywhere. We give the Young's modulus and the Poisson's ratio for steel and have that apply for elements 1 and 2. The geometry section is degenerate for this problem. I think it could even have been left out, but it's put here in a default way that we call for the geometry, and there'll be one such geometry set. And then this field of characters in here could have called out certain geometric properties that might have been needed. We don't need any, and we'll have that set apply to elements 1 and 2. And then that's the end of the data for our first load case. Now, because we want a second load case, we'll add another point load case, just one such case to follow, and we'll arbitrarily call it identification number 22. We'll show the point loads here of 0 in the x, 6,000 newtons in the y, 0 in the z, and no moments applied, and have that work on node 15. The final card will be a continue card that will be on the next page. The final data card is a continue card. Okay, then this run also was launched from an Apollo 3500 and sent to a Hewlett-Packard 700 machine, and then executed and brought back for printing. It only took a matter of seconds, something on the order of 5 seconds, to run these on the Hewlett-Packard machine, so it's an amazing power now available on the conventional workstations. Now, the displacement fields are the first thing to look at, and these points here are ones that are lying down at the pitch line or lower, so they are not the extreme values. So here the displacement's in the outboard part of the gear tooth, and as before we get the maximum deflections out here, out at the free end of the gear tooth, and I've marked those in blue here, so now I finally made a little sketch of where those occur, and this is for the aligned load. Then the vertical displacements here are greatest at points 22 and 23, but I don't regard that as very important. They're an order of magnitude less. These numbers compare very closely to the MSc NASTRAN numbers on deflection. For the misaligned load, we find that the maximum deflection is under the load at grid 15. And I show that here. Again, this number is similar to the MSc NASTRAN one, and that's the deflection as shown below here, right at the load. We're interested in the von Mises stresses in the gear tooth, and we've asked MARC to print these out at the nodes. So this set of stresses here, giving Mises intensity and then principal stresses, have been averaged already and presented node by node. It's a little different table than some of the other programs would give. We see that the highest stress for the aligned load in von Mises terms is 104 megapascals, occurring equally at 15 and 17 grid points, as it should because of symmetry. For the misaligned load, we have the following von Mises stresses. And we see here that at node 15, we get 357 megapascals for the maximum value in the gear tooth. This is more than 3 times as much as we predicted at the relevant grid points for the aligned loads. Let's prepare the ASTROS data now. We'll use 2 of the hex 2 elements. The connectivity is a little different than the other codes in that it progresses around the base and uses all 8 numbers there, and then progresses around this middle surface, and then finally on this top surface. Let's set up our ASTROS data. Our solution control cards are shown here. we'll assign a database, we put some titles on, and then in our analysis we're going to have basically two subcases that are static. And the first is the aligned load. It's originally a line load. And then the second is a misaligned load. In each case I have to ask for displacements, stresses, forces, and SPC forces. Now, the SPC forces, of course, are useful to determine the sanity of the solution and whether or not you are reacting the total set of live loads. Now, the bulk data is the same as for MSC NASTRAN. We begin bulk, and we have a grid set card. Let's define the grid points. We have 32 grids which follow on these next two figures. We use the default coordinate system as the basic right-handed Cartesian system. Then we give the x, y, and z coordinates. There's another default field here for the basic coordinate system in which we can read results out and have constraints applied and do intermediate calculations. Now, both of those are defaulting to 0, which is the underlying coordinate system, the underlying basic system. Here are the permanent embedded single point constraints in field 8 that are going to constrain the root of the gear tooth. Then we have the grids that are outboard and are not constrained. We need another figure of the remaining grid points. The connectivities come next. Here's the CI Hex 2 card that describes the first element, number 1. Now, it also calls out a property card here, which points down to the PI hex card below. That, in turn, calls out a material shown here. Well, the connectivities are given with the continuity on the next lines. We have these continuation fields that show that you need the 3 cards. Our second element defined likewise with the same PI hex property card. We're using the 0 again to get the stresses out in the basic coordinate system rather than a material or an element system. Here are the Young's modulus and the Poisson's ratio for steel, and we leave out the value of G. Here are the force cards. They're intermingled with the first load case being these arrowed ones. I've listed these in a node ascending order, and so the eccentric load got put here in the second card. And that's the end of the data. ASTROS prints out some interesting diagnostic information here. This has to do with the wavefront approach and shows a maximum wavefront of 20, which would be that for each of the elements taken separately. It shows an average wavefront of 12, which is interesting because for this smaller model, the connecting lines between the two elements apparently don't show, and then an RMS wavefront number. So this model is a little bit degenerate, but you do get the wavefront information out. I've collected the displacement information for the relevant outboard nodes for the aligned load case. And again, we get the maximum displacements in the y direction, and these are at the free tip of the gear tooth, much as if it were the tip deflection of a cantilever beam. Again, at nodes 26 and 30 by the numbering in this element. The displacements under the misaligned load are substantially higher. Here I have listed the nodes that are the outboard nodes, and the maximum deflection is under the load here at grid 15. It's about 2.5 times as much as for the aligned load case. Now let's look at the stresses in the gear tooth. The ASTROS code will give these stresses easily, and the octahedral shear stress will be the one that we're interested in. We can convert that to von Mises later for comparison with the other codes. The maximum stresses occur at these points shown here for the aligned problem, and we get values of 78.7 megapascals, both at the 15th and 17th nodes. That's projected from the element number 1 from down below, and then element number 2 up above projects values at those points of 48 megapascals. Likewise, we'll look at the stresses for the misaligned load case. And here the maximum stress occurs under the load point. And we get some 292 megapascals of octahedral stress at that point, projected from below. And we get 228 megapascals projected for that point from above. Those can be averaged and also converted to von Mises stresses. Let's gather our results now from the 3 commercial solutions and compare them. Here I show the undeformed mesh just for reference. Next I'll show the deformed gear tooth by using the NASTRAN results and the ideas post-processing. So these simple line drawings show the beam-like nature of the bending of the gear tooth in this problem, and then over here the twist that's put into the gear tooth by the eccentric load. And you can get some idea then that the